Okay, welcome everyone. This is Jim Sporer with ISSIP, the International Society of Service Innovation Professionals. And it's my pleasure today to introduce the uh, panel on industry transformation for energy and IT. And let me share my screen and I will get the presentation going. Can you see the presentation?
Yeah.
Okay. And I'll ask everybody to stay on mute. Other people will be joining, but please stay on mute. And if you have questions or comments, please put them in the chat. This is a series that ISSIP has been doing this year. We started with healthcare in May, did finance, education, retail, hospitality, supply chain, and logistics. And now we're up to energy and IT. And I just want to say that my colleague Vital Prabhu is traveling in India at the moment, and so he may be delayed joining us. Um, I would like to just make a few introductory remarks before I introduce our panelists. We have Meghana Puvati from NVIDIA. We have Marianne Piet from Berkeley Labs. Thank you both for joining us. Tony Helming will be joining us shortly, and Dinesh Verma is an IBM fellow and a colleague of mine from IBM days. Um, and I see Bert Painter, one of our ISSIP ambassadors on. Bert, you always ask great questions, so thank you for joining us. Um, and let me just make a few introductory remarks before I'll turn it over to our panelists. Each of our panelists will have 5 minutes to present their position statement, and then we'll go to Q&A. So uh, as you know, energy and information technology are in the news together a lot. In fact, there was this recent Gartner post that said, there's going to be an energy shortage in data centers because of all the explosion of AI. And if we look at the industry transformation measures, the cost of computation keeps going down, technology amplification capabilities keep going up. And of course, there's concerns about energy and the climate in all of this. Jensen Huang, the CEO of NVIDIA, uh, gave a great talk at Stanford a few months ago where he talked about the marginal cost of computing going to zero. And of course, in the ISIP community, as we think of the cost of computing going to zero, digital services that are coming out. Um, Two of the technology amplifications capabilities that we're seeing are uh, robots and digital twins. And if you haven't looked at these videos, take a screenshot snapshot and watch them. They're both fascinating, the advances that are happening. This is my version of Moore's Law. You can see if, oops, let me mute someone. Okay. Okay, everybody's muted. Thank you. Um, This is my version of Moore's law, and you can see we get to an exascale, which is the computing power of the human brain by about 2060 if the trends continue. This is one of the old supercomputers. A few years back, it was the fastest supercomputer in the world. It wasn't quite an exascale, but it was using over 13 megawatts. The human brain uses about 20 watts, so we have a long way to go. And certainly energy and information technology are in the news. I love this quote from the Wall Street Journal: using AI to summarize an email is like getting a Lamborghini to deliver a pizza. And so there's a lot of efforts these days to try to minimize the computing power used by AI. And this is one of the chips that some of my colleagues at IBM are working on. With that as an introduction of the connection between energy transformation and information technology, I'd like to turn it over now to our panelists to present. Um, our first panelist is Meghana Pavati from NVIDIA. As you're listening, please stay on mute and put your questions and comments in the chat, and we'll circle back for Q&A. Meghana, I know you have to leave before the end, so if you could go first, that would be great. I will change the slides to speed that up, and just let me know when you want the slides changed, Meghana. But if you could introduce yourself, that would be great.
Yeah. Maybe you can switch to the next slide. As Jim mentioned earlier, I'm Meghana Pawadi. I currently work as Director of AI/ML Enterprise within IT organization at NVIDIA. The work that we do here at NVIDIA is completely around using generative AI and artificial intelligence to use to use and automate everything related to IT, be it search, be it the internal tools, hardware procurement, everything that we do in IT is now being revolutionized with the new AI technology. Maybe the next one. As I mentioned earlier, not just within information technology, NVIDIA as a company is wanting to use AI in each of these sectors, starting with information technology within all the hardware and software related services, and then within human resources, be it within HR benefits, recruiting, and all the information search and retrieval aspects for employees for the employee experience. And we are heavily investing into how we could automate and make our employees productive, both engineers and the leadership who manages these engineers. For example, if you take the life of a software developer, we wanted to see how we could help right from gathering requirements, looking into the Jira tickets, understanding the current scope of work, help with code generation, help with code reviewing, have AI assistants and co-pilots at every step, right in the tool where they are performing the activity to make them productive and to make them use AI without having to worry about security, data ingestion, or network transfer of data, the local tools to external endpoints. Our motto is to get the AI companions, AI assistants, agentic flows within the tools where they are working at. Similarly, some of the other domains where we are heavily investing is how to automate the supply chain activities. As you can imagine, just to have one end-to-end chip working, you have many other micro components to be assembled and gathered and delivered from the supplier to the middleman agency who does the assembly, and then actually deliver finally to the cloud providers and to the actual customers. So we want to leverage this in terms of demand, supply, allocation, and even for the delivery schedules to use AI that can build on top of the existing linear operation optimizations that are there in order to fulfill the allocation and demands. Similarly, we are using this into sales and marketing tools as well, specifically sales when there are salespeople who are going to each of these conferences, gathering customer needs, writing out trip reports. We wanted to have a meaningful AI assistant that someone can interact to understand what went well at a particular conference, what are the latest customer trends that we are seeing in terms of hardware packaging, software packaging, or the full end-to-end stack. We have developed this trip report assistant which can gather these reports, does a summary and can answer questions like what went well at a given event, what are the learnings, compare and contrast between the conferences, and give a detailed point blank answer to the user. Maybe next slide, Jim. Some of the tenets that we follow when building the production systems is ensuring that there is data freshness, that there is a constant ingestion and syncing API such that your data is fresh. We make our architecture extensible in a way that we have configurable placeholders to enable customizations, upgrade to newer models, upgrade to newer retrievers, upgrade to newer re-rankers and embedding models. And we are, although it is heavily invested into making chips, we do want to use smaller models where applicable in order to make sure these productivity assistants are more affordable and cost effective. With the new trend to integrate AI into every platform and every application, we observe that there are longer testing cycles to make version upgrades, to make model upgrades, to make architecture upgrades, since the end answers that we get There was a disturbance. So we do account for this larger test cycles, especially given the final answer generation is in natural language rather than structured approach. And we do pay utmost attention to integrate security, that is access control permissions, right from data ingestion to the permissions while converting into embeddings, and then back in the retrieval, and then post retrieval, and then also manage real-time permission upgrades that can be applied post retrieval before surfacing this information. Given that information is easily accessible through the AI assistance, security or the information which is previously obscure is now more easily available. So we are revamping our security architecture such that this access controls are percolated at every level of the architecture. Next one, Jim. And I'll end the slide giving few thought points on what we see with respect to the future of AI, specifically in information technology. Within NVIDIA and even across the community, we see that there is more enhanced search, conversational search, efficient and intelligent knowledge management system so that it's easily accessible and gives more concise answers. We automatically see the tools which can generate this content and curate this content in a structured and indexed manner that can be retrieved easily and can be retrieved specific to the questions to answer in a concise manner. We see sophisticated analytics and reporting tools such that AI is integrated not just within the data parts, but also in the analysis part and in the dashboarding, such that it gives easy to consume information to all levels of people. And like I mentioned earlier, even within the software development assistance, by here I mean right from design phase to implementation to deployments and post deployments to monitoring, we see the trend to have AI assistants and co-pilots at every phase of the software and general engineering development. As Jim mentioned earlier, going forward, we anticipate a future of having digital twins, as the picture says here. That is, we can have many more replicas of each of us who understands the concepts and context that we have and represent us in meetings, represent us at various places, such that you have many more replicas to do much more productive work and increase your productivity exponentially. I'll leave you all with that thought, and happy to answer questions after all the discussions.
Thank you, Meghana. And sorry for the few audio glitches there, but we made it through just fine. And thank you so much. And I think one of the important things on this slide is that the agentic AI with agents, which is trying to reduce errors a lot more, is even more computationally expensive than some of the generative AI today. So definitely we're going to see some increased energy demands there. Let's move to our second panelist now, and I'd like to welcome Marianne Piet, who's Associate Lab Director of Energy Technologies Area and a Senior Scientist at Lawrence Berkeley National Laboratories. So I will be happy to advance the slides for you, Marianne. Just let me know when you would like me to go to the next slide. And please introduce yourself.
Thank you. Before you go to the next slide, let me just say a little bit about the national labs and Lawrence Berkeley National Lab. There are 17 national labs around the United States. We're very fortunate to be having this a beautiful view of the San Francisco Bay right above the UC Berkeley campus. And we are the home of the first particle accelerators. Some of you may have seen Oppenheimer and Ernest Lawrence, and we are named after Ernest Lawrence, who helped found the lab in 1931. The Manhattan Project didn't start until 1941, so we were doing a lot of physics. Now we're a multi-purpose lab with over 4,000 employees. Go ahead to the next slide. So I want to talk a little about our work related to data center energy use, but also help you understand our work related to the use of AI in the energy technology space. In the energy technology space at Berkeley, our primary client is the US Department of Energy, and we work in buildings, industry, transportation, electric grid, energy storage and conversion like hydrogen. And there's AI in all of those fields emerging. And I'll talk a little about some of those examples. I am not showing you graphs from the report to Congress on data center energy use. Armand Shahabi and Sarah Smith in the picture here will be releasing that report by year's end. It it talks about the fact that in 2023, data centers accounted for about 5% of the national electricity, and that's going out to about 10%, 27, 28. And then beyond then, we're of course looking at what is going to happen, and are the data centers that are being planned going to be built? So we're working a lot with electric utilities, which I'll talk about in a moment. But we're very interested in bending that curve on energy use, and I'll talk about some of the things we're doing to consider that. It is important to recognize that we actually have a model of every data center in the US. So we actually have shipment data from NVIDIA, and we're tracking CPUs and GPUs and trying to understand the energy use. This is the third report in 20 years on this topic. So there was one in 2016. So we've been doing this for a while, and we have a center of expertise at Brown, data center energy use. We are very interested in things like 24/7 carbon-free energy, which some of you know. And I'm actually involved in research in California, where we're trying to enable the use of AI to allow devices to get electricity prices from the grid and change their electric consumption if they have the ability to shift and shed load. The picture there shows in the middle of the day in California, we have something called the duck curve in the spring. So we have clean energy when there's plenty of sun, and we have more expensive energy around dinner time, around 4 to 9, when sun goes down. And that's a California shape. In Texas, where there's a lot of wind, it's a different shape. So in general, the cost of electricity is correlated with how much renewables are available. So in many parts of the United States, the price is cheaper when there are more renewables. There's a particular shape in Vermont, a particular shape in Texas. So we're trying to encourage buildings and transportation and EVs to charge when the grid is cheaper and cleaner. That's true of data centers, and it's one of the topics. I have a list in front of me of the research topics that are going to be in the report to Congress. So I'll talk about some of those briefly before I go on to the next slide. We're looking at producing this report more frequently. So we want to make sure that we're tracking what we know about data center energy use and working with electric utilities to understand what it needs to handle this load growth. We had a workshop recently with Google, Microsoft, Dominion Energy in Virginia, EPRI, about load flexibility, and can data centers actually be flexible? Today, a lot of the backup generation is diesel. Sometimes people are starting to use energy storage as a backup. And can the load itself be flexible? We've thought about the fact that maybe training is more flexible than inference. So we're starting to try to understand load flexibility. How efficient are the algorithms? How efficient is the cooling system? So there's a lot of work being planned around trying to bend that curve on the load growth and trying to support utilities. So when they're building this new load, they can actually collaborate with the utility and the hyperscaler to reduce the impact on making electricity more expensive for folks that might be paying for the utility upgrade. So normally all ratepayers pay, but there are efforts to try to create regulatory frameworks where the hyperscaler is more involved in building out this new load, and it's a dedicated load for them. So there's a lot of innovation we have never seen in our regulatory world at the states, this kind of load growth. And what does it mean for the need to serve new load, and how to protect ratepayers from that? So it's a very interesting time in this field. So we're working to try to balance and risk and cost allocation with data centers through these smart contracts. And we're working on creating data sets to help utilities understand what these loads might look like. And as many of you know, some of the loads are very spiky. Go ahead to the next slide. Just really quickly, I'm going to walk through some of the ways that we're using AI in the energy sector. There's tremendous potential to reduce energy use and emissions with the use of AI. So that we've talked about digital twins already. There's a huge investment around materials discovery. In grid planning, utilities are using the hourly data from customers to try to better understand load growth. And there's a lot of load growth in the distribution system from electric vehicles and heat pumps. So that as we electrify a lot of new loads, utilities need to understand how to build out the distribution system for load growth, whether that load growth is heat pumps in buildings, EVs, new manufacturing facilities, and data centers. The picture here is from buildings fault diagnostics. So in the circle are things that we measure in buildings: chillers, boilers, rooftop units, air handlers. We take that time series data and we compare it with a digital twin to see, are there faults? Is there energy waste? And we're starting to apply these tools for data centers. So do they understand where there might be energy waste, and managing with 6 kilohertz data, sometimes very high frequency data, what the peakiness of loads is. So we can look at performance and understand fault diagnostics to improve the maintenance, improve the comfort in buildings, improve the energy performance of these systems. Industrial process control, there are huge opportunities with digital twins. In cities and in transportation systems, we help monitor extreme heat in cities. And what can we do with cool walls and cool surfaces, cool roofs, to try to mitigate extreme heat with climate change? So fault diagnostics, industrial process control, and all of these things are really great opportunities for the use of digital twins. And we see them. I didn't mention the materials discovery. We've been mining text in journal papers for years, trying to understand new materials for batteries, for hydrogen electrolyzers, and moving beyond lithium to things like sodium ion. Go ahead to the next slide. So I provide you with just some links to some of the things that we're doing. In the energy technologies area, I have the link to ETA. We have over 400 staff doing work across, again, buildings, industry, transportation, grid, and energy storage. The California Load Flexibility Research and Deployment Hub, we're working on communicating with devices. We use a variety of standards. I myself was involved in something called OpenADR. So we work on EV charging, pool pump communication, thermostats, integrated heat pumps, ceiling fans, heat pumps and EVs, and thermal energy storage with predictive controls. We're doing a lot of work at the UC San Diego campus and many of the campuses here in California. I put a link to my Design the Future podcast, which is an interview about where some of this work is going. And then the labs themselves have been getting together and thinking about, how do we use AI for energy technologies to help decarbonize systems in the United States? And there's a story here about how we contributed to a new report on AI for energy. That actually came out last year out of Argonne National Lab. But the labs are continuing to explore how we create the understanding of the opportunities to invest in AI for energy technology. So I'll stop right there.
Fantastic. Thank you so much, Mary Ann. This is a great setup for our next panelist, Troy from EarthGrid as well. Let me stop sharing because I think Troy said he was going to run his own slides. And thank you again, Mary Ann. This was great, and those links are great too. Look forward to your podcast where we can learn more, and look forward to that new government report that's coming out. And fantastic that you're going to be thinking of doing them even more frequently as we go into this next intense phase of AI and data centers. So Troy, do you want to introduce yourself and take it away?
Yeah, I'll do it. Appreciate it. Thanks, everybody. And yeah, great tie-in. So I'm going to be talking about EarthGrid. So from using AI, the last two speakers to, improve things. Well, we also need to put more steel in the ground, and EarthGrid is a solution to accelerate the transformation to clean energy. So a little bit about me. 30 years developing and building companies in clean energy and infrastructure, including Tradewind Energy, which became the largest wind energy developer in the country. So I've had multiple exits and a couple of unicorns. Trade and Wind is now part of Enel Green Power, which was the #1 wind developer in 2017, #3 in 2018. And then I did a bunch of solar. And the biggest impediment to the growth of renewables is the antiquated grid. So I think we all know this, preaching the choir here, but the grid needs a $20 trillion upgrade to support the energy transition. And some say it needs to be, upgraded 2x to 3x, maybe even 5x in terms of how much. And I think we all know this on the call, but the grid in North America was at one time and might still be the largest machine ever built in the world. And now we've got to increase it by 5x. It's a massive undertaking. So also underground power lines, the European grid is 50 to 80% underground. The US, we're only 8 to 20% underground, which means our grid is actually not as reliable as it should be. But the problem is putting, power lines underground is historically expensive, but we got to do it, right? Permitting issues, are challenging. Severe weather are causing all kinds of problems in the grid. And the thing that really drives me as a solar and wind guy for decades is 80% of all solar and wind projects never get built. They get abandoned after 3 years. Now it's up to 8 years of going through interconnection studies. And that's due to, grid bottlenecks, lack of transmission lines. By the way, if I had to ask a question on this call, how long does the average person think that it takes to build a typical overhead transmission line in the United States or in North America? A lot of you might guess 2 years, 5 years, 10 years, and the average is 10 to 20 years. Most people say the real average is about 15 years, and that's for projects that get approved. Overhead lines are causing most of the fires in Texas, California, and so on and so forth. Lines underground are 9 times more reliable than overhead lines, according to U.S. utility data, but unfortunately 7 to 20 times more expensive to build until now.
Can we go back to that last slide before? I'm sorry to interrupt. That one was really interesting. Yeah, I want to take a screenshot of that. Okay. That's interesting. That's something. Yeah, it's very interesting actually, because it's a topic that I was just meeting in Colorado with the state government about yesterday. But so I just was interested in how it links to energy transmission, right? So continue as you were.
My pleasure. No problem. Yeah, and happy to share this deck with anybody who'd like to see it. So our great labs, thank you, Marianne, but this one's from, again, Lawrence Berkeley Lab is doing great work, but this shows grid congestion. And if we had stronger transmission, these show some of the nodes where if we were able to improve transmission, this is the grid congestion relief value in dollars per megawatt hour from the report from 2023. So here's our tech. I invented this plasma tunnel boring technology about 8 years ago, and we've been developing R&D and machines and so forth. But on the left is a 3-torch tunnel boring robot. You see the 3 torches. On the right is a 2-torch excavator. So on the left is a tunneler. On the right is an excavator, which can dig ditches, carve out holes in the ground or caves, like wine caves or caves to put transformers or data centers in if they want to be underground. And we can bore through anything. The tech is fairly simple. We just create lightning in these tubes. Then we pass air, which is free, over that lightning, and it superheats the air into a plasma at up to 27,000 degrees. And that plasma turns rock into sand and gravel without the use of drill bits, cutting heads, chemicals, bentonite, lubricants, any of that stuff that can leach into our groundwater. So it's environmentally benign, and we can go faster and cheaper than anything else. And I'll get into that in a moment, but we're not going to sell our machines. Our business model is we have a sense of humor. So our products are Badass and Boom. Badass is boring and drilling as a service. So working with PG&E and many other utilities across the country to help them, make the infrastructure more resilient, bearing power, fiber, water lines, and things like that. And that's where that's our construction business. And on the right is our Boom model, build, own, operate, and maintain, where we own the tunnel and we lease out space or charge a toll to connect, say, a data center to a solar or a wind farm that might be 10 miles or 100 miles away with an underground extension cord. So we're up to 10 times lower cost, up to 100 times faster, lots of patent claims and so forth. And most importantly, again, that 10 to 20 years to get the permitting on a new transmission line. we can do that same line and get all the permits done in 1 to 3 years. So in terms of accelerating, not only are we cheaper and faster than it's ever been before, we can, the physical work, it's also much, much faster on the permitting side. Because if you go underground, you don't have the NIMBYs and the bananas that are going to want to slow or stop the project. They don't see it, they don't care as much. And I'll just move forward real quick because I know we have limited time here. So I'll go actually to this next slide. EarthGrid has been approved as a regulated telecommunications utility in 46 states and counting. So as a telco utility, we get essentially guaranteed access to the public rights of way to put our tunnels or trenches under any public road in any state where we are a utility. It's not a slam dunk, but it's a much easier process, and there's typically no public comment period. So again, we can get the rights of way and the permit, and sometimes in a matter of days or weeks. Usually it takes a few months. And then the last thing I'll mention here is that we signed a few months ago a huge joint venture, an $18 billion joint venture funded by the Kuwait Investment Authority, their group Enertech Holding, to build out an underground supergrid. And we believe that with this $18 billion budget, that we will be able to enable 500 gigawatts of new solar and wind to come onto the grid. And of course, we'll need lots of AI to help manage the interplay between our network and the existing network. But we're very excited about that. And that's it. So we believe this is world-changing technology, and would love folks to follow us and help us change the world.
Thanks so much, Troy. This is great stuff. And people can start putting comments and questions into the chat, and I encourage our panelists to look at the chat and answer them anytime they see them. I'm going to start sharing my screen again and ask Dinesh Verma, IBM fellow, to introduce himself. You can kind of see how we stacked this a little bit. We included the IT at the beginning with Meghana, and then we put some of the energy and IT kind of in the middle. And now we're going to go back to IT with, and these slides and recording, of course, will go up on the ISSIP YouTube channel and SlideShare probably tomorrow. But Dinesh, if you could introduce yourself, and I'm happy to advance your slides for you.
Thank you, Jim, and thanks for this opportunity. As Jim mentioned, I work at IBM. I'm an IBM fellow working at the research center. I have been working there for a long time. I graduated from Berkeley 32 years ago, and after that have been at IBM more or less all the time. I also moonlight, or actually volunteer, at an open source group where I'm the CTO for Enterprise Neurosystem Group. Can we go to the next slide? So the current work that I'm doing, which is most relevant, or my focus for the last several years, has been trying to build AI application in the area of distributed systems and networks. One of my current projects is what's called the Natural Language Interaction Protocol. The good news is that today ECMA approved it as one of the technical committees to formally standardize that work. I'll talk on the next slide about why I think that's really an important piece of work and why it changes. I've also worked on using AI to understand network traffic, built a whole bunch of federated learning enterprise applications using AI-based systems, and created self-management systems. So I've got a reasonable number of accomplishments along the way. But what I would really like to share with you is my perspective on what is AI, what can AI do, or more importantly, what can AI not do, and what do we have to do to unlock the true potential of AI. So can you go to the next slide, please? So now we have AI everybody has heard AI and how great it will be and how it will do that. And as an engineer, basically, I would like to assert that unfortunately, most of that hype is not true. AI is fabulous technology. AI is great technology, but every technology has limitations, and AI has its own limitations, and some of them are very significant ones. One, especially if you look at almost any, say, IT services or business services or enterprise services, the key fact remains that AI in itself is not the end in itself. AI is a means to an end. And the end is to deliver some kind of business service. The business service could be something that fixes your chiller or transformer early. But in that cases, the cost of delivering an AI-based solution has to justify its advantage and benefits it gives. For example, I worked a long time building an AI-based solution, which will essentially monitor a chiller and a motor and effectively, inform immediately when the fault happens and alert the person. And when I tried to actually put it to the production, the guy who was actually operating this chiller said, okay, I have to put all this equipment in and the monitors and so on, which is fine. Happy to do that as experiment. But you are alerting me of a fault in a few minutes. But guess what? This thing fails. This equipment that I have is built so reliably with so many things. It fails maybe once in 5 years. And people come and service it on their own on every 6 months. And honestly, if it fails, I'll notice it in 6 hours. So you're saving me 6 minutes instead of 6 hours. In the 6 hours, I don't lose a whole lot. So from that perspective, that certainly made me realize that even though I could do a better job using AI, for that particular domain, the value delivered by AI was not enough. And for all of the important problems that we have in the enterprise, many of them have solved with effective solutions. We can put AI problems, but only a smaller class of those problems would be the ones that actually the cost of putting AI-based solution would be worth it. It's a decent cost class. It will still have a big transformation. So I'm not saying AI would not, but we shouldn't really, there will be a lot of cases where you'll find that the cost of AI-based solution would not be useful. Furthermore, there's a big limitations in having an individual AI-based agent. An AI agent can only learn, can only do and improve what it has seen, the patterns that it's seen before. It only learns, you only can do what things it has learned and knows how to handle the previous situation. The current AI agent technology is not coming up with new ideas, new things. And that basically thing, of course, means that I can build an agentic agent. I can build something system that sees data and learns and improves it. But learning comes at a cost. Learning comes also at a speed or slowness of the speed, because learning takes time and things. And essentially, we are coming up with one of those physical constraints in which if you build an AI agent, you can either build it at low cost, which will be an inference-only solution. You can build something at a really high speed, which will be inference only, or you can slow down the speed, have it infer and learn at the same time, or you can build the accuracy. So you can choose two out of these three: a really low cost AI solution, a really high superpower AI solution, or a highly accurate solution. It's very hard to get all three of these together. The other big challenge with AI, is AI is touted as a big cost savings solution. And the cost saving solution essentially is great for the first instance. But if you got $100 and you reduce the cost to $50, it becomes really hard to get the cost down from 50 to another $5 or $10. There is intrinsic cost of the system that won't go down, which basically means that on any agent, any system, you introduce AI, you get a one-time big value, but then after that, the value kind of flattens out. So now this doesn't mean, and now I'm not, do not take any of these to mean that AI doesn't have great value. AI is awesome. AI will do value, but these are the limitations of AI. And the basic limitation here is that a single agent, a single interactions has got limitations, which if you want to drive the really new value from AI in IT, in any industry, we have to create AI-based agents to understand new patterns, create new patterns, new things that will do. And you cannot do that in a single agent. Now, this is not a new phenomenon. We have seen something like picture like that in our lifetime about 30 years ago when the internet and web technology came in. We had distributed computing. We had a lot of automation that could make an individual server and computers do a lot of things, data processing faster. But the thing is that there was a limitation to how much value, societal value, can they deliver. Once we had a new protocol, the HTTP, Hypertext Transfer Protocol, which allowed these computer servers to talk to each other easily. Servers could talk to each other, clients could talk to servers at one time, and that unlocked the whole business potential, the whole social potential of web and internet technology, because these different computers could interact, and that interaction opened the aperture and created opportunity for new type of services, new type of things. It also disrupted a lot of business models in the 90s and the rise of the internet era. but it created tremendous business and social value. Now, if we focus on AI agent just as individual agent, will not be able to extract that much value. They will get down into the constraints because of these, we'll all hit the inalienable laws of how much we can get and how much value we can get from a single agent. Now, the way that you get new patterns, new interactions, new technology is by letting these agents talk to each other. And to unlock these potentials, you need a new standard. You need an equivalent of HTTP for the Gen AI era, which will allow the agents to talk to each other and unlock the new values. And I strongly believe that accepting and adopting that type of common standard by which these agents could talk to each other, AI systems could interact, would unlock the business and social potential of AI, generative AI, or the new technology much more than if we'll just look at an individual agent and try to optimize it. And of course, as it did in the HTTP era, the increase of these national interactions and among the agents is probably going to disrupt a lot of existing business models and create new business opportunities and new social value. And that is my prediction of the IT industry digital transformation from AI. So here's the contact information, and I have got the information about my own credentials, as well as those of you who are interested in following more details on this new protocol, the repository for the new protocol information. Thank you.
Thank you, Dinesh. Now let's open it up for questions. You can either type the question or comment into the chat and we'll go through it there. I want to first give the panelists an opportunity to ask each other any questions they have. I'm going to stop the share so we can see each other when we talk to each other a little better. And if down in the React button on the Zoom, if you click on that, there's a raise hand icon. So you can use that if you'd like to raise your hand. I'm going to go ahead and ask the first question to get things rolling here. It's going to go to Troy. Troy, an obvious measure for what you're trying to do is how many linear miles or kilometers have you created so far? Have you got a measure on that? And is that on an exponentially increasing curve year over year, or is it still too early to say?
Yeah, great question. So we are at this weird inflection point where we're 8 years old as a company, 7 years of R&D. We completed our first 3 projects in the last roughly 12 to 18 months. And we did, 2 kilometers on one, and the other 2 were smaller. So it's been a lot of R&D, and now we have 1 machine fully built, the 2-torch excavator, the 3-torch tunneler is going out in the field this spring. The projects we have booked next year, yes, it's going to be an exponential increase for at least the next 3 years. We hope to do something like 20 or 30 kilometers this coming year, and hundreds of kilometers the following year, and then thousands of kilometers the year after that.
Fantastic. Wow. Okay, thank you. And next question I'd like to direct to Mary Ann. Mary Ann, for the report that's coming out, you said it's going to be coming out before the end of the year. Are you going to be doing a podcast on that? Would you recommend that we watch your podcast or go read this big giant report?
Yeah, good question. So I wouldn't be doing the podcast. It would be Sarah Smith or Arman Shahabi.
Okay.
Arman he's already been at the National Academy of Sciences, and he was at the International Energy Agency last week talking about this report. So there are a number of stories but we'd prefer you sort of wait because the numbers have been moving around till we finalize it. We've already gotten a lot of press, and it will be, I think some of the key media outlets will be covering it. So there will be some summaries, and there's a briefing deck that goes through it pretty quickly, so you don't have to read it. So you will definitely be hearing about it. So thanks for the question.
Great. All right, let's open it up to others who have questions. You can either raise your hand or go off mute. And Troy, did you have any? Let me just ask Troy, did you have any questions for anyone?
Well, the other presentations were interesting. I guess my only question is whether any of those technologies would be helpful for our own private grid. Seems like they all would be, but maybe we can take that offline.
Okay. All right. And Marianne, any questions?
I appreciate Troy. I dropped in the chat a link to the Energy Markets and Policy, our group that does the work that from the graphic that you showed. That is one of the groups under me. We're also looking at reconductoring. That there are things to do to expand the capacity of the grid. And so if you haven't read about, we have a new, the REFA tool to help utilities look at the costs and benefits of reconductoring. So they can actually double the capacity of the existing grid by, using the existing infrastructure. And as Troy pointed out, it takes a huge amount of time both to build the renewables and to build out the grid. And that's a huge problem for the United States. I put a question in the chat for Dinesh. So Dinesh, we use a lot of white box models and black box models. White box are physical models. When modeling those chillers, we're interested in, there's a lot of physical models as well as data-driven. So we call them gray box models when you have combined them. But I really like your idea about being able to let the models talk to each other. I think that's a great idea. And certainly, in a lot of demand side or even supply side systems, these models are not linked to other models. So your technique, I think, will be really valuable. Have you looked at sort of physical white box models also? And I should say, we use the time series data to train those models, right? So we're continuously calibrating them, but I'll let you comment.
No, absolutely. So as you said, at least for the physical devices analysis and fault diagnosis, if we can get a white box model, or if we can get a physical model which is pertinent, that gives the best solution because that's the fastest and the most effective one. The challenge, of course, is that as systems get more complicated, especially when they have more components, while you can build the simple models for a few limited number of physical things, as the number keeps on going, the physical model and including the instability in the interaction of the model makes it difficult. And that's where, for more complicated things, when you have a lot more features and a lot more data, and it's not that, it becomes harder and harder to build the white box model. And that's where either you can call it the hybrid gray box model or the pure AI data-driven models become a lot more effective. And the complexity of the system that one is trying to control, manage, and monitor, that basically determines whether you have to move it. For most of the complex systems where, most of the practical systems that at least that I have in my limited experience, the physical model, just because there's so many components, the physical model is pretty much becomes much more harder to provide. That doesn't mean it cannot be done in certain domains. It's just that a lot more problems just require either a gray box or a pure data-driven approach.
Thank you.
Great. One thing that I thought was pretty exciting that came up in a couple of the talks today was this idea that policy is often the limiting factor in some of this, the time it takes to go through the laws, to get approvals, compliance, and I think that might be an area for us to look at in the future with the ISSIP community. So I don't know, Marianne, Troy, Dinesh, if you have any pointers on that, but or any thoughts on using AI for improving policy change, or but let me leave that kind of vague question to you all. Any thoughts?
Okay, I think that's an excellent idea. As a matter of fact, but this also means I'll sway away from pure technology to some politics also. The fact is that if you look at our policies, the way we make societal decisions or legal policy decisions, we are sort of following in some sense a lot of processes and practices that were developed a couple of centuries ago. Now, if you look at the power of AI, or even if you don't count AI, just the power of computing and simulations and other type of modeling techniques in general, you can do a lot better modeling of the different aspects of society. You can build a lot more technical aspect of thing, and you can actually come up with better societal policies just by using digital computation tools. unfortunately, and this is not to say that a computer can model all of society, but you can model a lot of the things and a lot of properties, and you come up with a better solution, which is optimally improved and is better. Now, what you can see, even for societal policies or economic policies or sharing policies, a lot of decisions are made by effectively, I would say almost politicians or demagogues, which basically are people who have a strong religious belief in some approach, as opposed to people looking at a engineering approach to solve the societal problems. Now, with the power of digital computation, the big increase in capacity we have, the big ability to model and derive, say, policies using some AI techniques like reinforcement learning and study impact, we can actually go to a much more engineering qualitative effect to both study the social sciences in a much more quantitative way and derive the right policies, or at least an objective policy, or be the able to do the trade-off of that. Will we be able to do that is not clear to me, because
Sounds
the
like it's
are
going to
not
take a huge amount of computing power and a huge lot of energy to do all the Monte Carlo of all the different actors. But thank you, Dinesh. I agree with you.
it's actually way a small fraction of the actual what we use to train a single AI model. So it's
I see that Leslie Tom has her hand up, and unless Marianne or Troy have anything,
Well, I have a super quick comment about your question. There's a lot of complexity in energy regulation. So state energy regulators have there's the filings, like the material. So I have thought about, could we feed those into large language models to help them look at what are other regulators around the countries doing. So essentially what we're trying to do is identify best practices. Regulators have to think about affordability of energy, the cost of energy, equity, environmental issues like air quality. Troy was talking about undergrounding and reducing the fire risk, which is happening here in California, and it's expensive, and so we need to reduce the cost of undergrounding. Regulators regulate cost recovery. What can a utility invest in? We have investor-owned utilities, municipal. So you can think of the grid as the largest machine man has made. These AI things are catching up, but I think there's a role for AI, but I don't know what it is yet.
Thanks. Okay, Leslie, if you want to come off mute.
Oh yeah, sure. Hi all. I'm Leslie. I'm the Chief Sustainability Officer at the Charles H. Wright Museum of African American History in Detroit, Michigan, and I just really appreciate this this event, Jim, that you've pulled together. Our museum is considering to be working on an energy exhibit by 2027-28, and I would love to start to be able to take some of these concepts of the past, present, and future of where energy is going or heading and how we consider it. Also, Autodesk has been partnering with us, and we now have a complete digital twin of our museum, being one of the first smart museums that we have sensors and Internet of Things all kind of working. And so what I'm trying to do with my service design lens is figure out all the jobs to be done of how to take care of these building equipments, like, so Marianne, like you're talking about, like the chillers and the heat pumps and these sorts of things. But I would love to just be able to, from like a third grader perspective, be able to collect the type of artifacts. So like Troy's, like some of your boring equipment, like how can we create a traveling exhibit that might travel to different museums talking about energy. And what's interesting is it'll be about the 25th anniversary of the Northeast blackout. So really being able to like connect, how the grid really affects people's lives and how we can all work to consider our set points and these sorts of things. So Yep, just wanted to thank everyone.
Great, thanks. Thanks,
Uh,
Leslie.
So Leslie, I would love to connect. I have a researcher who actually worked on the reliability study of from the Northeast blackout, was funded by DOE to study that, and I'd be very interested in your traveling exhibit. So let's connect offline.
Okay, great. That's great. Thanks.
Wonderful. I have 1,000 more questions for the panelists. I could just monopolize this, but let me create a little space for somebody else who might have a question. And if not, we've got like 5 minutes left, and I'm going to start firing away with a few quick ones.
Jim, it's Bert Painter with a socio-technical systems background or perspective to this. I gather Meg Hanna has left us. Is that right? Because one of my questions was for her.
Yeah, unfortunately, she got pulled away, but she said if we have questions in the chat, she would respond.
Okay, I'll leave it in the chat.
For her.
Yeah, but I mean, it was great information in the other presentations, from my perspective anyway, about how AI and energy management and network and engineering can reduce energy costs and increase energy efficiency. But I'm wondering, what else, like the nature of computing, do we really think will reduce the cost of the huge growth that we're going to see in the use of energy in order to use AI? Is there something about the nature, in the same way that I saw some mention about a new IBM chip, but there's got to be something in that area of the whole nature of computing which transformed data processing and had its other effect on our ability to calculate and so forth. That's my question for our technical friends.
Well, I know Marianne's colleague Horst Simon worked closely with Dharminder Mota and some of the people at IBM on the low energy chips, and I know that's an active area of research to get low energy chips. And you know, I think that's got to be, you know, if the human brain can do an estimated exascale at 20 watts, and these data centers are doing exascales with megawatts, clearly, you're right, Bert. There's a missing innovation somewhere here, and you know, and you think about you know, just the energy requirements that could be saved if we could make a breakthrough there. You know, we didn't get into quantum computing, but some people are claiming there's going to be a big breakthrough in quantum computing.
Yeah, that was one of my questions too. Is quantum computing going to make a difference that way?
Lots of fertile ground for future ISSIP events there, Bert. So thank you. I will mention that on the policy stuff, you're probably aware of this, Bert. The Santa Fe Institute has a group that's doing some interesting work on building models of decision making in larger structures, socio-technical structures, and policy making and things like that. So that's interesting work. We might do a future event on that. We only have 2 minutes left, and I want to really thank the panelists, one and all. I mean, I'm just, you know, the brain power of our panelists just is always awesome. And Troy, your as a service model is so appropriate for the ISSIP community. Thank you so much. And Marianne, we're out here in the Bay Area, so I hope we get a chance to meet sometime at some IBM Almaden event out here. Maybe we'll get Dinesh to fly in for that from the East Coast, but and maybe Meg Hanna from NVIDIA will come over. I know she works closely with Rama Akkaraju, who is an IBM fellow who's now over at NVIDIA. So thank you all. I hope you all get connected. James Mister, thanks for joining. I know you're doing a lot of venturing for Bavaria in this area of energy. I see Alka Roy, who does responsible innovation, is also on. Christine Leitner, who's looking at AI policy for Europe.
Thanks, Jim.
Lots of good people here. Connect up and do great stuff and make us proud. So have a great holiday as well. And thanks, everyone. I appreciate it. And I'll get this recording uploaded and the presentation uploaded probably tomorrow. Thanks, everyone. Have a great holiday.
Take care.
Thanks, Jim.
And thanks for the inspiration on quantum. I'm meeting with the founder of Inflection tomorrow, Jim.
Excellent.
Dr. Dana Anderson. So Inflection here in Boulder.
Wonderful.
But we'll chat more. Bye-bye.
Or bye for now.
Bye.